Okay, so we've been looking at the Laplace transform. We've looked at what the Laplace transform is. We've looked at certain properties of the Laplace transform itself. We looked at certain special types of functions for which the Laplace transform can be evaluated using the properties, and how that can be exploited to find the Laplace transform of composite functions, right, in which involve various standard types. Now, so in this lecture we will look at what is called the inverse Laplace transform, right? So it's important to be able to go back, right? So we know how to take a function which is defined for positive times and go to its Laplace transform. Oftentimes the other direction is also important, right? So typically we are imagining taking a complicated operation in time domain, as electrical engineers like to call it, and when you take a Laplace transform, you have reduced the complexity of the problem. Typically we're interested in looking at something like an ordinary differential equation, which is a comparatively harder problem, and then when you go to Laplace transform domain, it becomes an algebraic problem, and then you can solve for the unknown in this domain where it's an algebraic equation. Solving an algebraic equation is an easier problem compared to a differential equation. But then once you have solved in this Laplace domain, you have to come back, right, to the original time domain which is where you want the answer. So then you will have to carry out an inverse Laplace transform, right? So that's the subject for this lecture. We look at how to find out the inverse Laplace transform for certain standard functional forms. Okay, so like we said, the Laplace transform finds its application in taking converting a relatively hard problem into a relatively easier problem. For example, converting a differential equation into an algebraic equation. You solve for it, and then it's really a complete solution only if you can come back to your original domain, which is the time domain, if you wish. And so that involves taking this thing called the inverse Laplace transform. So the problem of the inverse Laplace transform is the following. So if you're given a function f of s, so the problem is to find a function f of t such that the Laplace transform of f of t is f of s, right? So we write formally as f of t is equal to L inverse of f of s. That's the problem which we want to work out, right? So the method we take here is actually a sort of brute force approach, which is we just form a table of standard types, and then we just look up from the table and see if we can bring the function that is given to us into one of the forms here, and then exploit some of the properties of Laplace transform to be able to work out the inverse Laplace transform, right? So we don't have like a formal approach here, but rather it's like a lookup approach. You find a table, collect all. There is an extensive collection of Laplace transforms of various functions which has been made up, but we will look at a very simple table based on mostly on our own direct evaluation of some of them, but also there are other types which we have put in. So let's look at this table of Laplace transforms which I have collected here. So f of t, if it is 1, we know that it is just 1 over s, and e to the at, we have seen it's like a translation in the Laplace domain. So it's 1 over s minus a. Sine of bt, we have seen b over s squared plus b squared, and cosine of bt, it's b over so cosine of bt is s over s squared plus b squared, whereas sine of bt is b over s squared plus b squared. Likewise, we can also evaluate the hyperbolic sine and hyperbolic cosine, right? So you see that it looks somewhat similar, except that some sign involving the b squared part will change. We worked out how to compute the Laplace transform of t to the n. It's just n factorial divided by s to the n plus 1. Then t to the n times e to the at. We saw it's like doing a translation in the Laplace space. Then t times sine of bt, we can work out it's 2bs divided by s squared plus b squared the whole squared. Likewise for t times cosine of bt. And then we can also work out e to the minus at times sine of bt. This also is like a translation in the s space e to the minus at cosine of bt, but it's convenient to put them all down in a table, right? Because the forms which appear on the right hand side are standard forms, and then when you have this form you should be able to work backwards quickly. And then I also collected sine of bt minus bt cosine of bt, so divided by 2b cube. The Laplace transform of this is of this form, 1 over s squared plus b squared the whole square, right? So you see that on the right hand side you get all these standard algebraic forms, right? Oftentimes this is what we work with, and then these exponentials also come in. Exponentials, you can try to tweak it and introduce special kinds of exponentials of this kind using the Heaviside step function. So t times sine of bt divided by 2b, this is very similar to this one of these earlier ones. So we already saw that 2b t times sine of bt, so Laplace transform is 2bs over s squared plus b squared the whole squared. So indeed t times sine of bt divided by 2b will have the Laplace transform s over s squared plus b squared the whole squared. Then we saw that theta a of t has this Laplace transform e to the minus as divided by s, and we also saw this property that if you have a translation of this function in time domain, it gives you e to the minus as in the Laplace domain times f of s, right? So all these properties combined with some other properties also which we will discuss are very useful for working out the inverse Laplace transform. So the technique is simply to take your function whose inverse Laplace transform you need to find and bring it into one of these standard forms, and then that's it, and then look it up and write down the answer for the time domain function. So let's look at a few examples. So this is best understood with the help of examples. So f of s, suppose it's given to be this kind of a quadratic form, 1 over a quadratic form. So you must massage it into one of the forms here. So we immediately see that you can write this s squared plus 2s plus 5 as s plus 1 the whole squared plus 2 squared, so which comes in the denominator, and then you might as well write it as 1 over 2 times 2 divided by s plus 1 the whole squared plus 2 squared to directly mimic a standard form here. And then we look up the table and we see that in fact the inverse Laplace transform of this function is half, which we have pulled out, times the inverse Laplace transform of this function, which is nothing but e to the minus t times sine of 2t. So e to the minus 1t comes from this s plus 1 the whole squared. It's like a shift in this Laplace domain, so you get this e to the minus t, and then sine of 2t, the 2 corresponds to this 2 here and this 2, right? So you have to just be careful that you bring it exactly into the right form and work backwards. So that's example 1. Let's look at another example. So suppose you have some algebraic expression. In the denominator you see that you have s power 4 plus 4s cubed plus 3s squared, but this s squared is something that you can pull out, and so you can rewrite this as 7s plus 3 divided by s squared times s plus 1 times s plus 3, and then it's in this complicated form, but we should write it as a partial fraction so that we can bring it into one of the standard forms. So the partial fraction technique tells us that you should be able to write this as a over s. Look at all the factors. So you have s squared, so you must account for both a over s term and a b over s squared term, and c over s plus 1 and d over s plus 1, where a, b, and c and d are coefficients to be determined. So can we find coefficients a, b, c and d such that these two expressions, the left hand side and the right hand side, agree for all values of s? And in order for this to happen, we should match term by term. S cube term will vanish, so that will give us a plus c plus d equal to 0. Then the quadratic part will also vanish, because in the numerator you have just 7s plus 3. So 4a plus b plus 3c plus d, you can cross check this, must go to 0. Then you have 3a plus 4b equal to 7, 3b equal to 3, solving which you immediately get b equal to 1. Therefore if you plug backwards, right, from the bottom up, if you go, you get a also is equal to 1, right? So 7 minus 4 divided by 3, that's a is 1. And so you have these two equations in two unknowns, c plus d is equal to minus 1 and 3c plus d equal to minus 5. So you can solve for it, and then you just simply get c equal to minus 2 and d equal to 1. So finally f of s can be written as 1 over s plus 1 over s squared minus 2 over s plus 1 plus 1 over s plus 3. You should cross check this, right? So typically doing this partial fraction expansion entails some human error, and so it's always a good idea to cross check it after the final step to see if indeed we have got it right. And once we have checked this, it's just simply a matter of looking up from the table and writing down the answer. So the inverse Laplace transform of this function now, 1 over s will give you 1, 1 over s squared will give a t, 1 plus t minus, these two will just give us these exponentials. So minus 2 times e to the minus t plus e to the minus 3t. Done. Very simple. Once we bring it into the right form, it's just simply a matter of looking up the answer from the table. So let's look at example 3. So now suppose we want to work out the inverse Laplace transform of 1 over s plus e to the minus s over s minus 2 times e to the minus 4s over s. So now we see that this is connected to the Heaviside step function, right? So 1 over s of course will just be 1, but e to the minus s over s, the inverse Laplace transform is theta 1 of t, and minus 2 times inverse Laplace transform e to the minus 4s over s is just minus 2 times theta 4 of t. Done. That's the answer. And of course it may be convenient, in some applications to write this more explicitly in this form. So the function takes the value 1 from 0 to 1, and it becomes 2 from 1 to 4, right, until this starts kicks in, and once this also kicks in, it just drops down to 0. It's like it involves 2 steps, right? So this is also something that you should cross check. So let's look at another example. Suppose we are interested in finding the inverse Laplace transform of this function e to the minus 3s times 2s plus 3 divided by s squared. So whenever we have a factor like e to the minus 3s, we should immediately see that maybe that can be incorporated in terms of a a step function of some kind. So let's just work out the Laplace transform, inverse Laplace transform of the other part, 2s plus 3 divided by s squared. So we have, and so we can rewrite this 2s plus 3 over s squared as 2 divided by s plus 3 divided by s squared, right? Each of these we know how to find the inverse Laplace transform of. So from the table we can say that inverse Laplace transform of 2 by s plus 3 by s squared is 3t plus 2t plus 2, 3t plus 2. And once we have this, we simply use the property that this type of a factor e to the minus 3s simply means that you have to tag along a theta 3 of t, but you have to be careful. It's not just simply 3t plus 2, right? If you think of this as a function f of t, you must find theta 3 of t times f of t minus 3, right? So the function itself must be shifted by the appropriate amount. So then you get final answer as theta 3 of t times 3t minus 7. You can explicitly check that indeed if you take the Laplace transform of this function, you get back the original function you started with. And if you want, you can also rewrite this inverse Laplace transform as, it takes the value 0 from 0 to 3, but it becomes 3t minus 7 starting from t greater than 3, right? Okay, so using these properties and with the aid of the table, there are many other functions whose inverse Laplace transform can be worked out. Many of these algebraic functions are what we will care about. So it's useful to play with these kinds of examples, so that when we do the the problem of solving ordinary differential equations using Laplace transforms, these inverse transforms are essential to be computed. So if you are very comfortable with these techniques, they will come in handy when we look at some of these applications. Okay, that's all for this lecture. Thank you.